kind of important, and then in 2 minutes I really will be talking important things, so try not to be late. It's now 9:15. The other important things I want to tell you is that when I came here 36 years ago, there was no physics department at the Weizmann Institute. There was chemistry, biology, and there was department of nuclear physics that I worked, right? And then it turned faculty of nuclear. Then it turned into a faculty of physics with the department of nuclear physics and other physics, and then nuclear somehow disappeared. And so, like 35 years ago, of course, that many people would be in the course of nuclear physics and not of information theory, which nicely tells you the period we are living, what kind of phase transition. We are less and less interested in energy and more interested in information. That's more or less a process which takes last 200 years, but it's really accelerated now. And some people still think that they have nuclear energies, but it's so yesterday. Right? It's the real power is information. Okay, but still, I'm telling you this story, which is essentially a story about understanding restriction on our possible actions and descriptions. Those restrictions, as we'll see, they follow from our ignorance, but it was recognized 100 years after people started to discover these restrictions. And of course, the first restrictions was discovered about work, about energy. And then somehow it took like 200 years to understand that the same type of restrictions, they actually restrict our ability of perception, of computing, of communicating. And that's why most of I would teach 40 years ago, 30 years ago as physics and mechanics, I'm now teaching most of it as information theory. It's the same subject. Okay? But it took me for some, I don't know, 30 years to realize, and then I remember this epiphany I had sometime in the 90s when I was teaching just standard statistical physics, advanced statistical physics here at Weizmann. And then I realized that, no, I want to tell it differently. I don't like these paradoxes. All this idiotic. I mean, there are no paradoxes. It all must be trivial. The moment you teach something as full of paradoxes means you don't understand what you're teaching, right? When you teach something which is trivial, then it's powerful. And it was like epiphany. I said, wow, I'm a genius. And then I discovered here a book here at Weizmann, written in 1965. And this was like 95, 96, by a guy named Katz. It's a very thin book, which is called Statistical Physics as Information Theory. Exactly, he was teaching it. Like, he was a very colorful guy. He came to seminars with his dog. Very personality. Anyway, so let me remind you, as at every beginning of the lecture, I'll remind you the previous episodes, but very shortly, right? So what we discovered, what we discussed, that the first idea of restriction came out of a very simple setting of how much work we can do extracting Q1 from a reservoir with T1 and losing Q2 into reservoir with T2. And a young 20-year-old genius said that it is the inequality which bounds it. You cannot make Q2 smaller than something, right? That was the restriction, fundamental restriction, formulated in terms of the most basic properties of the system. There were no statement about coal or oil or wood here or anything like this, or configuration of it. It's a very, very fundamental and very abstract description. And then this quantity was later defined as entropy, namely the change of heat divided by temperature. And so it all started as thermodynamics, namely something about exchange of heat. And then it was formulated a very beautiful phenomenological discipline, which we now use over and over and over, applying to like everything we can just. Any moment we see a new system, we build the thermodynamics of it, and then we try to do more microscopic description. So this thermodynamics is essentially very fundamental and phenomenological description of any system, which tells what restriction you can impose on it based on its most fundamental quantities. And it says that the most fundamental quantity for any system is it has something conserved. For example, you have molecules exchanging parts or some polymerization processes coming. You say the number of monomers is conserved quantity. It can go from this macromolecule to that. Or system interacts, they can exchange energy. Well, energy is not additive because there is an energy of interaction. So if you bring two systems, you say, okay, we'll pay the price. We only consider system with short-range interaction. We only consider very large system, which is called thermodynamic limit. And so we'll say that approximately energy of combined system is a sum of energy. Then we can say that the energy is conserved, like you take this system, you take this, you take together, energy is the sum, you take some energy from this system, gives to it, the sum is still the same. And so the first law of thermodynamics was just energy conservation, which was stating that in the following form, that there is a visible part of energy change, and we can measure it, so we know for every state of a system what is its energy. But sometimes we measure the change of work, how much system did, and we look from which state it came to which state, and we see that here the difference is not equal to this work. We call the difference heat. Heat is an invisible part of energy change. Invisible in the sense unmeasurable. Okay? And that was the first law of thermodynamics. And the second law of thermodynamics is essentially a picture. It says that there is a quantity, some quantity, and it's a function of energy, just defined. Energy could be amount of money on the stock market, right? It's something which subsystems exchange but not create. And it's a function of energy. And there is a curve on this plane, and this curve is convex. That's very important. Okay? All possible states are below this curve. That's second law of thermodynamics. If you leave system alone, means that there was some internal restriction, you relax all of them. There was your system, it was composed of different parts, you let them very long time to interact, exchange energy in all possible ways, and then the system, being at the same energy, goes to the maximum of entropy. Okay? Question?
Yes, additivity is also part of the second law, or is it something separate?
What?
Additivity of the entropy is also part of the
second law is essentially based on additivity, but at its face value, just treats a given system.
Okay.
You say, take a given system, not interacting, but it may consist of many different things inside. So when you leave it alone, it starts, just this traders trade to each other, these molecules exchange monomers. There's a lot of things happen, right? Heat flows from one side of a system to another side of the system. You wait long enough, you come to the maximum of some mysterious quantity called entropy. By the same token, looking here, you understand that convexity actually tells you that you can reach any point of the boundary, which is your equilibrium. Okay? So this is your equilibrium state. Only in the equilibrium state there is a definite relation between S and E. Here it could be any S, right, up to maximum, but you can also reach coming to the minimum of energy under a given entropy. And again, if there are mathematicians among you, there is a beautiful mathematics which just from this minimax, it's just unbelievable rich world of ideas. Okay, good. So this was essentially general thermodynamics. Now, how it helps you? You say, look, I'm interested now in this very simple case where my system consists of two parts. So it is E1 and E2, and of course the first law of thermodynamics tells me that whatever happens dE1 is minus dE2, so they can only exchange energy, right? And I'm asking, so what is essentially the state of this system? So for example, I know that this is 2/3, for example, filled by one gas, and this is 1/3 filled for another gas by another gas, so I know something about them, and I want to know in what E1 and E2 they will live. Because in principle they can be at any state. One system can give almost all its energy to other. And I'm not talking now about fluctuations, but you can imagine that they interact. So I'm asking, what is this? And second law answers the maximum of entropy. Okay, good. How I find this maximum of entropy? Well, first of all, you say that when I'm changing energy, there is a changes of entropy on this curve. So I can introduce dE ds under everything else constant, namely volume, number of particles, magnetic moment, charge, whatever. I mean, number of people in the room, just whatever, everything else is, yeah, I change my entropy, and I define it as temperature, or by the same token, physicists prefer to do beta, which is dsd, okay, which is one of the temperature. So now, when I say that the change of an entropy of my system, I'm just briefly repeating what I did last time because I think that these are highlights that you are supposed to remember. So this would be dE1 ds1 over dE1 plus dE2 ds2 over dE2. And of course, this is minus dE1. And of course, this is 1 over temperature. So what I'm saying is this dE1, 1 over T1 minus 1 over T2. Okay? Which tells me that, of course, because entropy change could be only positive when I am in not equilibrium, then this positive, namely this system getting energy, means its temperature is less. Makes sense. So this positive, right? This is less than this. On the other hand, equilibrium means T1, T2, which already I want to notice you that the statement of equilibrium in terms of a fundamental quantities means that some derivatives are equal. Okay? Derivatives are. And of course, derivatives being, essentially it tells you that this is a total derivative of my total entropy with respect to my energy, which must be zero in equilibrium. Well, it's maximum, right? So its derivative must be zero. Okay? All of thermodynamics here on one lecture. So I was telling you like this, give you all thermodynamics. Okay, question.
This formalism, what is the definition of entropy?
Something which reaches maximum at equilibrium. That's how you do phenomenology. Something. There exists something. And again, you are a scientist now, right? So think about how would you be a 19th century or 21st century person doing thermodynamics of conscience, for example, right? You're saying, what is this something? What is this something that always getting increases under this type of processes? And you're very empirical. And you aren't thinking about axioms, you're thinking about some changes, right? Good. So what is entropy? Asked Boltzmann in 1870, whatever, two, I don't. Not sure, I must check. It's in his grave. The formula that I'm now about to write is in the Vienna cemetery. It's a very beautiful place, maybe most important in Vienna now. And on Boltzmann's grave it's written, well, it's written without E, but I'll write it this way, okay? So what Boltzmann said is that let's now try to connect entropy with the properties of the system. So look at a given system and ask yourself what could be entropy. And he's postulated, and then he returned to thermodynamics and have shown us that all the thermodynamics make sense under this assumption. They say that entropy is just a logarithm of the possible number of states. If you are interested in the entropy as a function of energy, just count how many ways the system can have this energy. For example, if you look at the system, you just count how many possible ways to divide energy between, I have a finite energy, and I can divide them this way, give zero here, whole energy here, just, So your entropy is a logarithm of this quantity. Okay? So now this gamma, it's a kind of a traditional notation. It's a Greek capital gamma. So, well, how to count, right? And for example, let's just treat this simple system in this way. How many ways to divide the energy between these two systems? You Boltzmann now, right? You have a right idea, but now you need to show all these unbelievers outside that it really makes sense. So you need to write formulas, computable. So how many ways to divide energy between two systems?
You need to quantize it before.
Exactly. Infinite. You want a finite number. That's why, I'm a classical person, but my arrogant friends who do quantum physics, they always say, what are you talking about? I mean, your science did not even exist before H bar appeared. Come on. What kind of course, you need to, and then what the genius of Boltzmann was understanding that it does not matter. Interdynamically. So what essentially Boltzmann said, let's say that our energy goes in quanta of delta, no H bar. Okay? Which essentially is very interesting how fundamental ideas appears as technicalities. And then it takes like 50 years to understand that it's actually a fundamental idea and not a technicalities. Well, look, imagine that I measure my energy with an accuracy delta. It was a very natural thing to say, in 19th century, the mid-19th century, for about 100 years until Kolmogorov, it was very natural to say that, okay, let's consider that we have some finite accuracy, and then we'll turn it into zero at the end of computations. And essentially, you will see that the result of our computation would be not very much dependent. So, essentially, we may say that now we can count, right? So this state, this system can have zero, then this would have E. Well, let me put it this way. So there would be like E 0, E minus delta, delta, E minus 2 delta, 2 delta, all the way to 0 E, right? So what we now need to compute, we need to compute the gamma of our whole system, right? And it will be, still not very, so, and it will be a sum, well, kind of idiotically large sum from I equal to 1 to E over delta. So this is a number of steps, right? Well, actually, from 0 to I over delta. And so you take gamma 1 at E I, and you take gamma 2 of E minus EI. What is explicitly assumed in this formula already?
That energy is conserved.
Huh?
That energy is
It's, first of all, it's assumed that for every term in the sum, it has the same total energy. But there is more to it. Look, there is a number of states of a system 1 at a given energy times the number of states of a system 2 at remaining energy.
The number of states in one system doesn't care about the
Yes,
states in the other system.
yes. At this point, look, there is still no probability. Boltzmann was doing it a little bit different, but I want to kind of walk you my own way, and the probability appear in the second hours today. So at this point, we're just counting number of states. We aren't saying anything about any. People really hated the word probability at this time. So it's just a statement of independence of the system, namely that for a given number of, for a given state of a system 1, the system 2 can have any state compatible with this energy, right? So this is the energy which 2 has, and it's just, so you compute this kind of independent. Of course, we would now call it statistical independence, but at this point it's just kind of number of states. So it's possible to have a state of a system 2 no matter what is the state of a system 1 as long as energy is there. Okay? Now you look at this formula. Well, this is 10 to 23 kind of some of order of magnitude, right? Something Avogadro scale number. So what do you do with this formula?
Take log the left.
Take log. Well, this is why people take logs, incidentally.
Because it will make it additive.
It is additive and
Yeah, because we are lazy, we don't want multiply, we like adding things, right? At the moment we started to do big computation, which was essentially 18th century, we invented logs because it's much easier to sum numbers. But at this point, it's not that we are lazy. You want to take logs and they will be less before you take log. And it's very idiotic to take log of a sum. You like to take log of a product, right? But you have a sum of products. So you have many products. You want to take a log. That's the right direction. All this course will be taking logs. But to take a log, you need to go from a sum to a product. And then you take a log. Okay? So how you get rid of other terms in your sum? You have a feeling.
The biggest term in the sum.
You ask exactly what Boltzmann asked because you're looking at an extremum, right? You're looking at equilibrium. You're trying to find this equilibrium. So you ask, what is the largest term of this sum? Okay? For this, which means what largest? What energy corresponds to this? The only variable here is energy, right? It's delta, 2 delta, 3 delta, 25 delta. So you ask, how many deltas I need to take so that more or less this would increase with delta, this would decrease. Somewhere there will be a balance, right? You look for maximum, you differentiate, right? Good, so let's differentiate. So you say that if I differentiate d gamma dEi, it's d gamma 1 over dE1 1 times gamma 2 plus d gamma 2 over dE2 gamma 1. You can write it as gamma 1, gamma 2, ds1 over dE1. This is still assumed, right? So the derivative of gamma I can express as the derivative of an exponent of s minus ds2 minus dE2. Why minus? Because again, dE2 is opposite to dE1. Here it's minus and here is plus, right? So when I differentiate with respect to this, so this would give me negative derivative, which would stand here. And of course, the extremum correspond to exactly the same statement T1 equal to T2. But now, thanks to Boltzmann, we understand what this extremum means. It's the extremum of a number of states. So just equilibrium distribution of energy between two parts is where the most ways to realize this partition, right? Essentially, that's what Boltzmann explained to us, the combinatorial meaning of a thermodynamic statement that the temperature must be uniform across the system. Okay, and now you can say, okay, look, so now I know what is the largest term here. I know the total number of terms. So now I can restrict my phase volume between its, let's call this defining E1 and E2 equal E minus E1. Namely, this would mean in a while, in the next hour, will be mean value, but for now it's just equilibrium value, right? This is what corresponds to this. When this is 0, then this is equilibrium value. So now we can say that if I take out of this sum only the term with equilibrium value, that of course is estimate from below of my total number of state. And if I just take this term, gamma of E1 and gamma of E2, and multiply it by a total number of terms, that would be an overestimate of mine, right? So if all terms will be equal to maximum, that would be my value, and if only one term I would remain, that would be my value. This seems like a huge kind of very unbalanced estimate until, like you suggested, we take logarithm. So if you take logarithm now, so you say that your entropy is bounded by S1 plus S2, and here it's S1 plus S2, again taking at equilibrium energies, plus logarithm of something, or logarithm of E over delta. So now Boltzmann says that, of course, and I mean, what we are doing the last 50 years, we're of course working in a non-thermodynamic limit, we're working with nanoparticles, we're working with macromolecules, so this is not a huge, and this is not a huge number. But the moment you are in a classical thermodynamics, this is order n, E over delta, because your entropy is extensive, right? So this is order n, and this is order logarithm n, and this is relevant. Well, you might stay arguing, people of course took a bit pleasure out of it, you can turn delta into 0 and it was kind of goes to infinity, but this goes to infinity faster than this, right? So in this sense, with a logarithmic accuracy, as physicists like to say, you really live in an equilibrium state. You can look at your entropy and estimate it from an equilibrium state, and you know now the meaning of it, what it means equilibrium. Equilibrium means maximal number of possibilities. Okay? There's questions here. I want you to meditate looking at these two formulas because it's basically elementary, right? But
Can you explain again the second equality, the second line?
what I'm saying is that
No, one line above.
this one, this I'm
No.
saying,
Even one line above. Yes, the second equality there.
this is a definition of extremum. So I ask for the derivative to be 0, which means I'm asking what is the largest term of this sum. The largest term of this sum is when this derivative is compensated by that derivative, right? You can imagine gamma as a more or less growing function of E, right? So as you increase the possible energy of a first system, you increase its number of states, but you decrease the number of states of a second system, and somewhere these two processes come into balance. And then you go down again because you will be decreasing this faster than increasing this. Okay? So essentially, this is a very general consideration. There is no specification of a system. It's an elementary but very important point. I really want you to look here, right? You need a genius to do such things, but when it's done, it's really kind of elementary. Right? So with a logarithmic accuracy, entropy defined as the logarithm of a number of states is indeed extensive quantity, it's additive, and equilibrium just corresponds with the usual definitions of what is temperature, etc. Okay? Are we good here? Everything is down from here. We're already at the summit. Okay, all the other stuff. Good. So let's compute something, right? So that's what I promised you, that it's, let's now take the simplest. Well, people used to think that the simplest is the ideal gas, of course not. The simplest is just a set of two-level systems, which is now, of course, of huge importance because, brain is essentially Ising model. It can either fire pulse or not fire pulse, so it's very easy to describe it by being up or down, or in state of 0 or state epsilon. So two-level system is really kind of probably the most now abused and overused. So let's see how non-trivial it actually is. And so I say that I have a system which could be in a state of energy 0 and in a state, well, how I call it? Let's call it epsilon, right? So I have n such particles. Each one can be in the state. And then I say, okay, for this system with this n, if it has energy E, it means that there are L, E over epsilon which are in the upper state. Right? So every energy E means that there is L here and n minus L here states. Right? Good. Now when I try to compute entropy as a function of energy, what I need to compute is just how many ways to choose out of n particles, L particles which are, well, just choose L particles. They are all indistinguishable, and I don't care which particle is in excited states. You can think about it as atoms in your laser, so some of atoms are in an excited state and some in the ground state, or you can think about spins, and some spins look up and some spins look down, or you can think about neurons, and we'll have a separate lecture, it's called Ising model of the brain. So you say, okay, if neuron is firing at the moment, we call that it's excited. If it's quiet, we call that it has zero energy. So now what you need to compute is, it has a special notation. How many ways, and you've seen it, of course, I'm sure, how many ways to choose out of n L particles. It's here what we start is a combinatorics. There will be two ways of thinking. One will be very, very discrete combinatorics, and another will be very fluid, continuous way of phase space flow, etc. It's like your left and right hemispheres of your brain. But now combinatorics, you all learn some combinatorics. Or you want me to be slow here? How you feel about it? Number of permutations. So I have m I need to choose out of m particles how many ways to do permutation between them. Okay? So the formula is very simple. You say in the first position I can choose any out of this m. What remains for the second position for any choice here is m minus 1 that I can choose, m minus 2 that I can choose, 1. So this product is called m factorial, and it's a total number of permutation of m identical objects that you've seen, right? Now, out of this simple formula, we say that we can now build this number, which is called binomial. We say that we need to take a total number of permutations. That just, if I would just take all and not permute. But we're not interested in all of them. We need to diminish them by the fact that we already have L in this state and n minus L, and we aren't interested in permutation between them, right? Whatever. So we need to divide it just by these two things. And this would give you the total number of choosing, and this is our gamma, as a function of energy or as a function of L, right? So entropy is just a log of it. Okay? This is all the computation is here. Let's plot it. You already see in your mental internal space how this curve looks like. So I plot now S as a function of L, which is just energy in a dimensionless units. And my S is a logarithm
logarithm of n factorial L factorial n minus L factorial. And just for the heck of it, we know what is 1 factorial. And what is 0 factorial? Also 1. Even just kind of, just for the sake of simplicity of the formula, this is the most natural definition. Good, okay. So now of course you know what is this. This is logarithm of this minus logarithm of this minus logarithm of this. So when I have L equal to 0, my energy is to 0, namely all my particles are in a non-excited state. So what I have here is unity, right? What is the logarithm of unity? Good. You have a point. Now, of course, I have the same. This is apparently symmetric with respect to n over 2, right? So if I take here n over 2, then just by changing L is n minus L over 2, and this is n minus 2, that will be the same formula, right? So essentially, when I choose, it doesn't matter whether I choose L in this position or L in this position. It's still L, n minus L. Then it's clear that, of course, at n it's also 0. It's clear when L is n, this is 0, and this is n, so this is unity, this is 0. Okay? And I know without any Stirling formula or computation that this curve is convex. So now, just being a simple mind in physics, I'm sure this is something like this, right? What else? Well, sorry, I'm my power of drawing. Okay. Indeed, it's a convex function. It nicely demonstrates you that already this simple system has, what is this?
Negative temperature.
Negative temperature states, namely, entropy decreases with energy. When I have overpopulation of this upper state, again, I define energy as being positive here. So when I overpopulate, you see my L is larger than n over 2, when I overpopulate the excited states, my temperature is negative. And people got Nobel Prize for it. This is not a simple, at 70s, when I was a student. It's not a simple matter, right? Now we'll discuss the physics of it. So, of course, when you look at, let me remind that the temperature is dE, ds, and of course, we physicists like beta, which is ds, dE. But what you find out is that here's your temperature are positive. What is your temperature is a little bit to the left here. The derivative of entropy with respect to energy is almost 0, right? You're at a maximum. This means that your temperature is very, very large. This is kind of plus infinity temperature, right? Or this is why we like beta. Beta smoothly goes through 0, right? Usually, when you do real statistical physics, it's a lot of beautiful analytical complex analysis. It's all analytic functions of betas. Okay? And then temperature is minus infinity here. Okay? Now, why we have a negative temperature? Technically it's kind of trivial. You just decrease the number of possible states because you are overpopulated. You have too much energy and too few possibilities. But could physical systems be like this? Spins. People who got Nobel Prize for it got it for spin system and paramagnetics. And why you need to give Nobel Prize for something which seems like a trivial thing, right? We just computed it. See, it's negative.
It's not trivial that it exists not only on the whiteboard.
Yeah, and so now you go to a real world and you say, look, I want two level systems. And of course, people now go to, brain and they see negative temperature state all over. So people go to stock market, they see negative temperature state all over. But back at 70s, we were still poor physicists. So what we had physical systems. But so don't we have spins in physical systems? This is just a system of spins. Why it takes Nobel Prize to get it experimentally? And why physical system, real physical system, opposite to markets or other things, always have positive temperature in equilibrium.
There are not two levels usually. There are many levels usually.
In this case, you can imagine there are two levels, but there are other levels that still you can make it overpopulated, and that still you can consider the distance from the first excited level to the other level really large. The difference is that usual physical system not only has this type of energy, right? For example, usual physical particles have kinetic energy, and kinetic energy cannot be negative, right? And in a moment, in the next lecture, when we write Boltzmann formula, probability of energy is exponent minus energy divided by temperature. The moment you have a negative temperature here, let me just write it so that you appreciate how dramatic it is. So the Boltzmann formula, Gibbs formula, which we're about to derive in the next part, is like this, right? When this is negative, this is positive, which means infinite probability of infinite energy. It's totally unphysical. So what happens, and when you can have negative temperature state, is when you can really isolate your degrees of freedom, in this particular case, nuclear spins in external magnetic field, from the other degrees of freedom, namely that your atoms actually moving, right? And that took very low temperatures and the Nobel Prize for the measurements, right? So it's really only when you treat part of your degrees of freedom as really detached from the rest, then the energy of this part degrees of freedom can really decrease entropy when it's too much energy. Okay, so that's kind of the reason. So now imagine that you take this system, which is being isolated, let's say here, have a negative temperature, and put it into thermostat. Okay, so I took my set of spins in a magnetic field. There are too many spins looking in the wrong direction. Namely, it's a system what is called inverse population, as laser people like to call it. And you maintain contact. Namely, you just wait long enough, and system will be in contact with your environment. What will happen?
You suck energy.
First of all, you need to equilibrate with its thermostat. To equilibrate with the thermostat, you need to have a temperature which is equal to the temperature of a thermostat, right? But the temperature of a thermostat is always positive because it consists of real particles, not with particles with which only some degrees of freedom. So you need to go here somewhere, right? Into whatever the temperature of a thermostat, let's say, is somewhere here. So you need to go this way. In this way, like you rightly say, you go, what happens to your energy? You go from right to left.
Decreasing them.
Which means laser generates light. That's exactly laser. That's another Nobel Prize. Okay, so what you find out in this sense that negative temperature is higher than positive, right? In that curve, just the convexity guarantees you that when you take a system with a negative temperature and you equilibrate it with a thermostat, it gives away your, and you can even do it quasi-statically, namely very slow, so that it passes through minus negative temperature to the plus infinity positive temperature, and then to the final temperature of the thermostat. You see?
Why do you need convexity for it?
Well, you need convexity for stability. Convexity is just something which is the ground on which you stand. The moment there is no convexity, you fail and your system breaks. There is no system if it's not convex because it's actually broken in some other system which are your elementary blocks. Okay. So I want to stop here. Question?
Yes, but we said that energy flows from high to low energy, so shouldn't we go right because we add energy?
In positive temperatures?
Okay.
Again, this is a very good question, so let me remind you the formula. ds was dE1, 1 over T1 minus on 1 over T2. When this is... Okay, some people have not seen the first, or some people have been, I recognize it, but some people have not been here on the first lecture. You've seen a record, you haven't seen a record. They of course, mixed up as usual happens, so that in the first installment, there were first 20 minutes was not recorded of the first lecture. Okay? And if somebody have not seen it, I'll just briefly reiterate that first of all, it's a graduate course. So questions are very important, answers are something which you are expected to give immediately. You see, it's a very interactive stuff, and so there is no wrong answers. That's what's really the difference between student and researcher. The students are focused on giving right answers, and the researchers are focused on honing your instrument, your intuition. That's why it's very important when I ask you a question, immediately give an answer. Maybe just in your head, and then start thinking. That's the only way that you develop your intuition. Okay, this is very important. So apart from all this information theory, I really want to train you how to do research. And in research, the most important thing is your own intuition, how different you are from other people. On the other hand, if you really give an answer aloud, you're giving a huge service to all other people, because you start seeing how other people think, right? So it's a very interactive, and also it's a course in which there are people here from different faculties, even not only departments. So I want you to interact, right? I've given a mini version at Berkeley, and there was a girl who was doing some kind of a transcription, kinetic for freedom factor and biology, and there were guys who were at physics doing quantum computing correction code. And when I made them talk to each other, they recognize they are mostly, optimizing the same two-term function of which we call free energy, right? So talk to each other, but also it's very important that treat it not like you need to, get a right answer or you get a bad grade, right? Wrong answers are very important because they train you. You give an answer and then you ask, why the hell I say this? And that's how you learn about this instrument, okay? Good, but now we re-recorded the first, so there is now a recording of the first lecture, which with 20 minutes also installed, and there is a book. I mean, this book, students gave me this t-shirt as an appreciation a few years ago, and the book was written. Anyway, so all the problems in the book, you're supposed to solve them, but the book has detailed solution for all of them, right? Exam will be a couple of problems of the book. Well, font free, I hope, etc. But it's really, I hate books without solutions, so there are all solutions are there, but try to solve it. The problem more or less start from elementary and then kind of less elementary, okay? So there is nothing which is not in the book, right? There's no reason to make note, etc. It's much more important to interact with me, to listen my questions and to give your, genius or idiotic, they all are interesting, your answers, okay? So let's do interaction. Good. So now, let me again return for a moment to thermodynamics and recall that thermodynamics has kind of different ways of description. One way was what we like to call microcanonical, namely when we were focusing on a thermodynamic potential or the function which gives you extreme, which was entropy as a function of energy. Or energy is a function of entropy, which is kind of just a function. But then we say, okay, look, it's very technically would be useful to consider temperature as an independent variable, and temperature is a derivative. So, and then we ask the question, which is called the subject of Legendre transform, how you actually can come from the function which is E of S to some function which is a function of t, and t by definition is a dE over ds. So what is this function? How you need to be related to that function so that it would be one-to-one correspondence between this function and that function. Okay? And we realize it's just taking E and substituting here S expressed through T would be wrong, right? Because that would correspond that, for example, if you have kind of some function y of x, and this is a slope p, which is dy dx, then that curve would give you the same relation between the slope and y, right? And so we want to pin this curve. We say not this curve, right? And so what we do, one way of pinning it is Legendre invented. He took this function, take this point where it crosses this vertical axis, and you can define it as psi, which is e plus, which is y plus dy dx times x, which is px, right? So this is this y consists of two parts, this part and this part, and well, psi consists of y and this part. So you can say that what you really need is psi, which is y minus px, or in this particular case, we say that you define a free energy, which is E taken as S, re-expressed through temperature minus Ts, right? So what is important here is that it is now a function of T, which is a derivative, right? S is also re-expressed through T, but it's subtract of extra term. And this is, again, second most important formula of thermodynamics. It's called free energy. And we discussed why it is called free, right? Again, every important thing has a name, and this name is extremely important. It's usually genius invented it. And then we realize that, at least while we are at thermodynamics, is a part of energy which we free to use keeping temperature. And it turns out that it's less. Now in 21st century we say our ignorance decreases the amount of work we can do at a given energy. Or stock market people say our ignorance decreases the purchasing power of our money, and the less we know, the less we can buy by the same amount of money. Or people now in communication reinterpret it, but it's the same idea that having a finite temperature in a system somehow restricts your ability to do work, or communicate, or compute, or whatever. We'll see how it appears over and over and over again. Okay? So this is a very important, it's still thermodynamics. We just made a Fourier, a Legendre transform from one function to another. It's one-to-one correspondence. df is dE minus TdS minus SdT, which is TdS minus PdV plus mu du n minus TdS minus SdT, which is minus SdT, and then plus mu du n plus work, right? So now you see that the partial derivative of entropy with respect to free energy with respect to temperature is minus entropy, exactly like temperature was plus derivative under V n constant, dE ds under V n constant. So, of course, the Legendre transform is invertible, namely, if you look at f as a function of t and want to come to a new variable, which is a derivative of f with respect to t, this new variable will be s, and you come back to your E of s. Right? So the Legendre transform, you can go like Fourier, you can go forward, you can get the same formula up to a sign. Here it's minus, here is this. Okay? Again, you'll see in all this language of Legendre transform, namely passing from extensive variable to intensive variable, the huge importance of convexity. this is only possible for a concave or convex function, but the function of which second derivative does not change a sign. Namely, any first derivative value has a one-to-one correspondence with the function itself. Okay? So convexity appears and reappears all the time in what we are doing. Okay, that's thermodynamics. And of course, you all learned it. I just wanted again, standing on I really hard to remind you this part. So now we'll do the thing which Boltzmann did to this function, namely he said what is the entropy of a given system. He says that S is a logarithm of gamma. We now want to look at this description, which now a description of a free energy as a function of temperature. Or physically, we want to look in a subsystem inside of a thermostat, right? And ask what is actually the formula of computing entropy. If we know what is the system, let's say, two-level system, okay? So that's the second question.
There we have S as a function of T, but we define only S as a function of T.
Where you mean where? Here?
Last blue term, yes. Oh, yes, also.
Yeah, what I'm saying is that the moment that you made this definition, this is a formula. Look, this is E of S, right? So the right function is a function of S. It expresses S in terms of T. You just need to invert this equation. Okay? So essentially, when I'm saying this, is just an inversion of this relation, as usual. But what it tells you is that to rightly define the new function, it's not enough to invert this and substitute S in terms of T. You need to add, you need to fix the shift. You need to nail your curve so that it would not be sliding, in this direction or in this direction. You do inverse transform. Okay, so now I really want to physically look like this. So I have a big reservoir and it has gamma naught, it has some energy naught, and I have some subsystem inside. So what it's really when you're a scientist and you kind of live your life and you want to understand with what tempo, great discoveries are made. It's very interesting to look at history. So you can just imagine Carnot's 20s, first law of thermodynamics, Joule and Meyer, 42, 43. And then 50s, late 50s is Clausius and understanding of entropy. And then like 20 years, like a quiet. And then at 70s, there is an explosion, namely Boltzmann and Gibbs with a difference like 5 or 6 years, and Maxwell, of course, at the same time. So like nothing happens 20 years, and then everything happens in 4 or 5 years. That's how it usually works, on such a great scale. So it's very interesting to know the dates. So we're now 1878, I guess. And of course, the genius of Gibbs was, it was not that consider system in a thermostat, but what really kind of impressed, I still, when you read the first edition of Landau, and it's like 50, 60 years after Gibbs, we're still in awe of this idea that he treats the thermostat as just n copies of this system, which immediately allows to do combinatorics and all this. Is just this simple idea that whatever the thermostat is just big system. So you can just consider it as n copies of our system. And that was okay. Anyway, so now let's first use the Boltzmann idea, but answer the simple question: what is the probability? I'll probably better use. This I would leave. So I would say, and the probability for now I would be calling it W, but then at some point I'll switch into pi's when I will do information theory. But I still keep like W's for physical probabilities and then pi's for like general vector. So what is the probability of being in some state having energy E for my subsystem? So it has this E. And of course it could be any now because it's part of a thermostat, and thermostat is a big system. So this can exchange energy with its different parts of a thermostat. So you ask, and this is the first time we start using the word probability. Okay? So what is the probability? What it must be dependent on? We only want it to be kind of dependent on this energy, right? But let's say what we know is, not know, but it is this big thermostat. So the idea which Gibbs naturally took from Boltzmann is that it's something about number of states, right? The Boltzmann idea was that system goes to maximum of entropy, and entropy is a logarithm of a number of states. So essentially was thinking in these terms already, which Boltzmann explicitly did, is that the most probable state is a state which has the maximum number of possibilities to realize it, right? This implicitly contains ergodic hypothesis, namely that all states are equally probable, and so the amount of energy most probable for which there is the most number of states in which it could be realized. So essentially the idea was that this thing is somehow must be proportional to the phase volume of a thermostat at the energy E naught minus E. Right? This is just an idea that what depends on E is that the larger this E, the less the energy remaining in the thermostat. Right? So you expect that it would be something, and you can of course assume that this is much smaller than this and expand. Right? How would you expand this?
Second order.
First of all, as Landau used to say, money in the exponent, right? So if you expect that you are having a very sharp function, and this function is exponential, is in the exponent, that the smart thing to do is to expand in the exponent. So you say that, of course, this is exponent of S naught E naught minus E. You can say, well, this is just technicalities. Or I can differentiate this, or I differentiate it's a logarithm of this, but it's a big difference, of course. Because now, I mean, this is, if this is a very sharp function, so now you would say that this is something which is, okay, let's just write it. So this is approximately exponent S naught of E naught minus E ds ds naught dE naught, which is inverse, right? So this is, one can say that this is an exponent minus exponent of energy over t, and then here you need to write something like normalization factor, so that if you sum over all possible E, so this Z would be the sum over all possible states exponent minus EE over T. What a beauty! There is nothing from thermostat except its temperature over here, which is what you need from thermostat, right? So thermostat sets the temperature. This formula tells you that the probability of a given state monotonically decreases with energy exponentially, and the temperature sets the range. Does it mean that the most probable value of energy is 0?
Among all states, but alone it is very important.
So it does not mean it. Why?
Because there might be some states with the same energy.
Yeah. Essentially, this is the probability of a single state having this energy. The probability of energy being E is a number of state of our system, not of thermostat, at a given energy, times exponent minus ET, well, 1 over z. Right? This is a fast growing function of E, this is fast decreasing function of E, and they create a peak exactly at E equal to T in a thermodynamic limit, etc. Okay? So, but what is really Important here is that we obtain now the probability of different state, and now we want to answer the same question which Boltzmann answered. What is the entropy, right? Because before that was an answer for microcanonical, for an isolated system. Now we have a system in a thermostat. How we define its entropy? Because now we can say this essentially the statement that this is a minus logarithm of W, because double I is just 1 over gamma. Right? So the probability of every state is a 1 over number of states. So you can reinterpret Boltzmann formula as minus logarithm of probability. But sorry, now probabilities are changing. I mean, this is fluctuating. Of course, there is some mean energy defined by the maximum of this expression. So now you ask, well, my entropy, what is this? I need to take minus logarithm of probability taken at a mean energy over here, or alternatively, I must take minus logarithm probability and average it itself, which means that it would be minus Wi logarithm Wi. Right? Namely, I am asking, this is a dilemma which Gibbs faced. So you say, look, I mean, Boltzmann had it easy, right? All probabilities was the same, so essentially the entropy was a minus logarithm of probability, which was the logarithm of possible states. Now I have different states coming with different probabilities. Should I average this probability over, should I average this log over itself, or should I just take it at an averaged energy? What would you immediately answer? What would be your choice? Nobody brave enough to say stupid things?
Not to average the energy.
Huh?
Not to average the energy.
Not this, or not this.
Not this.
Somebody likes both?
I
In the
will
thermodynamics.
somewhere check if it will give the same.
Yes. First of all, a moment your probability is exponential in energy, your logarithm is linear in energy. And an average of a linear function is an average of linear functions, right? Well, of course, they are the same. And that's why this is the importance of this exponential dependence, right? Of course, we know from here, we know that it's a very simple formula. S is, I mean, just look over here. It's E minus F divided by T, right? So somehow we really need to obtain it either from here or from here. We need to get, I'm sorry, kind of thermodynamics, right? But it is indeed important that probabilities are. So now let's compute this simple formula, and let's just do this. So here is my W, okay, and so I say that this is the sum of Wi. Take, well, logarithms. You know, until we come, this will be next lecture, to information theory, the logs will be like, normal. But from that point, it will be all in bits and it will be logarithm by 2, right? But for now, I'm just, and I'm not even use Stirling formula yet. So anyway, because, there is exponent and I like taking natural logarithm of an exponent, not divided by logarithm of 2. Okay, so you take logarithm of this formula, what it would give you? It would give you EI over T, that's an exponent of this, right? This is the VI and this is the EI at a given state. And then there is this logarithm Z, which comes out of this. And Z is just by definition, is what is defined here. So you immediately see that this is equal to e over t plus logarithm on z, and comparing it with this formula, you see e over t, and you say, okay, now I know what is this guy, which is called partition function. It is actually minus f over t. It's my interpretation of my probabilistic function. This is just a sum over my probabilities. This is just a normalization factor. This is its thermodynamic meaning. It's a free energy divided by temperature, because we'll use it over and over again. And so this is this formula. But on the other hand, you can take also the mean energy, and the mean energy, you get the same result. Just because it's so important, I'll rederive it in a kind of one more possible way, is namely that you can take, probably I'll take it from here. So you can take this formula, it's a definition of a partition function. I never understood the meaning of the word partition function, incidentally. I don't know, if you do it, you're welcome at the break to explain it to me. I never knew it. I learned it first in Russian, and it sounds even more idiotic, and then I learned it in English, and it didn't tell me anything. I don't understand in what sense it partition, etc. Just a normalization factor, which it would be called normalization factor, I would kind of like it, but it's called partition function. I never found a magic explanation why this terminology, which kind of bothers me still to this day. Anyway, so this partition function, you can take it and you can just differentiate it with respect to temperature. So let's take d dt of this relation, right? So if you do it, what you obtain, you would obtain z. So, right? Let me write again. So what you have z equal to e exponent minus f of a t, this relation, which is the same as sum over I e exponent minus ei over t. So I'm taking this formula and I'm differentiate. So I'm just trying to prove it alternatively, right? So I take this, I differentiate this with respect to temperature. Namely, it would be z itself times e over t squared, right? So it will be f of t squared minus 1 over t df dt, and this would be minus 1 over t squared. And now when I differentiate this with respect to temperature, I would get e coming into the sum, exponent minus e over t, and t squared, because I differentiate with respect to temperature. So you get this relation, you multiply it by t squared, and of course you obtain that your f is equal to e plus t df over dt, which is e minus ts. So why I was doing all this stuff? Because usually when I was taught all this was the relation, the relation between thermodynamics and statistical physics for microcanonical is this simple formula, and for canonical is this formula which I found not transparent. What I found more transparent is a simple statement that entropy defined as a logarithm of probability at mean energy is the same as an entropy defined as a mean logarithm of probability. And this last formula is the most important part of thermodynamics. So this formula is something which has maximum of application probably in the whole of physics. I don't think there is anything which physics gave to mankind is comparable with this formula. Okay? So now I really want to concentrate on it. So what it tells us, first of all, it's an immediate generalization of what we had before. So essentially what now when you look at Boltzmann, and instead of natural way of counting states, you just say that you're looking at probabilities. Well, if all probabilities are the same, it's kind of trivial. But now you say you're looking at probabilities, and you define a quantity which now you can define for any distribution. What is only important about this set of numbers is that the sum over I of Wi is equal to 1. That's it. So you have a vector, real vector, of positive numbers. We go to quantum mechanics, it will be complex. There is a lot of beauty. Like one great mathematician told me, physicists don't just understand what kind of a gem they have in this formula. It could be generalized for complex numbers. There are many beauties of it. And convexity, but the simple statement, for any vector of positive numbers whose sum is equal to unity, you can define this quantity. Any. There's nothing about equilibrium here. Or that these things must be like this. We all came here looking at physics, at equilibrium, and trying to find relation between energy and entropy. And what is often happens in science, we get a formula in which we can just kind of stop and say, whatever. We just look at this. This is formula which makes sense for any distribution. It took me like 30 years until, because when I was a student, they were teaching me entropy makes sense only in thermal equilibrium. And I'm a turbulence guy, what I do for life, I'm studying turbulence. And turbulence is very far from equilibrium state, right? And they were always telling me entropy does not make any sense away from equilibrium. Says who? Well, it took me 30 years to just get rid of what people, my great teachers told me and say, okay, why not? Whatever probability distribution I have, it always has entropy defined for it by Gibbs formula. Okay? This is why it's so important. And of course now, you can look at Gibbs and you can look at it as a particular case, indeed, of equilibrium. So let's now, any questions here? I'm now preparing, the next lecture will be just taking this formula and forgetting whatever we knew before, just and calling it information here.
I'm sorry, can you explain again why we say that the entropy is equal to the minus ln of...
Just let me. At this point, what we did before was equilibrium physics. Okay? We look at a system inside thermostat. We say, if we leave this system alone, that more or less what we can expect. That we can expect it to find it with a more probability if there are more ways to realize it. Okay? So we derive this formula. Right? Now then we look at this formula and we say, how we now would define entropy for this system? And we say, well, in the spirit of Boltzmann, we would define it as taken at an equilibrium value of energy, which turns out to be taken average over logarithm of probability. It's all well equilibrium physics at this point. What I'm now telling you, that it's starting from the next lecture, we just fly free. We say, well, let's treat this formula at face value. And the first thing I'll show you is just entropy of English language, and you will see that it is this. See. And there is no equilibrium. Or entropy of Ising model of your brain, it's computed by this formula. And you are not dead, which means you aren't in thermal equilibrium. Yeah. Okay. But still, I wanna finish this story. What's so special about this distribution if I look at this function? Okay, so let's do last exercise, because I usually skipped it and then people started complaining, and then more and more mathematicians and biologists were coming to the course, and I've realized that the method of Lagrange multiplier is not like as universally known as I expected. So let me now spend maybe five minutes on it. So define the definition. S is a functional of Wi's. For any set of Wi's, I defined S in this form, okay? You know what's the difference between functional and function?
Functional takes a vector or a function and returns a number.
Yeah. So function gives you number for number, right? And functional gives you number for function of a vector, right? Okay. So which means that you have a vector, but just one number, like 5. Okay. So for every vector, it gives you one number. And in a moment, it will be, of course, in log of theta, so it will be in bits. But at this point, I'm asking, is there something special about this Wi? So the question I'm now asking, this is this formula, and this is a very particular distribution. Okay? It says, now what you are given a set of these numbers. This is just characteristic of your system, it's energy state. And you ascribe probabilities in this form. Is there anything special to choose this form of probability related to this formula for entropy? And again, your energy mean value, as you probably can easily imagine, is just this one, right? Is there anything which relates these three formulas?
When those are the probabilities, then this is maximized, then the upper one is maximized.
Okay, so the idea is that this distribution realizes the maximum of this function unconditionally
Under the constraints.
Specific T.
under the condition that the energy is fixed. Okay? That's an assumption, or somebody can immediately kind of prove it. First of all, is this assumption looks plausible? That the Gibbs distribution realizes extremum of a entropy under a given mean energy. Because this is a probability, which energy fluctuates. This is a mean energy, right? It's not a closed system with a given value of energy. It's a statement that mean energy is given by this, is fixed, which is essentially temperature. Okay? Now, how to prove it? To prove it, you really need to take this S and vary it with respect to all these numbers. So there is W1, Wn, possible states, values of energy, right? Here is 1n, number of, I would rather take it n small so that we won't mix it with Avogadro numbers. And also it will be, next lecture it will be 26 number of letters in the alphabet. So now you need to choose all these numbers. Incidentally, there is also the sum of Wi is equal to unity. There is another constraint. So and there is a very beautiful method of finding conditional extrema. And that's what we'll be doing in this course. And what every algorithm in every AI or self-driving car or whatever is just looking for conditional extrema. That's what kind of most of the people now, not only in San Francisco, are paid to find conditional maxima of some function now, and it's usually in a very multidimensional space. So how you go for it? This condition defines a surface, right? In this n-dimensional space, okay, this is a vector, right? In this space, you can look for a maximum, but you say, no, I'm looking under condition, and condition means this surface, okay? So I want to look on this surface, on my maximum. Which means that while I go, and you are doing computer algorithm, computer people, right? You usually don't write formulas, you will just, Well, now you only just wipe coding. So you say, I'm going along this surface, and along this surface, I'm looking for the maximum, right? What does it mean? It means that on this surface, you have, as you go, right? You have a vector which is a gradient of entropy, and also the gradient of this energy. They must be parallel, because you go along constant this, right? And you want to find where the maximum of it. So you say, well, it's this parallel, there must be kind of, this is a vector, this is a vector. There is some kind of number which is sets their proportionality. But on the other hand, you also say that my derivative of wi's must be zero, which means extremum, means that the derivative of s with respect to vi's must be zero conditional on this surface. Okay? And of course, if you wipe coding, this probably does not matter. You just tell your AI to find you an extremum under this condition. But if you are a 19th century French mathematician, then you realize that it's much more beautiful to consider not a space of these n numbers, right? But just add to it extra parameter beta. So you now consider, I'm telling you Lagrange method of multipliers, which you all learn. Okay, I'm just kind of waking you up and saying that what we'll be doing a lot on this course. So you consider this kind of n plus one dimensional state, and instead of looking for the extremum of s, you'll look for the extremum of s plus beta e. Again, remind me, this, I just don't like this one. So your e is this thing, right? So you're looking for the extremum of minus sum of a wi's log wi's plus ei's. Okay. And now this is called Lagrange function, but you look for its extremum in this dimensional space, namely, you differentiate it with respect to vi for every I from 1 to n, and you also differentiate it with respect to beta, and you also require 0. So when you differentiate it with respect to, yeah, beta you have here, right? Okay. So when you differentiate with respect to beta, it gives you this condition, right? And when you differentiate it with respect to AI, it gives you the following thing. So let's look at this formula. You differentiate it here, for a given I, it would give you minus logarithm vi. When you differentiate it here, it gives you unity, which will be your normalization factor, plus unity. And when you differentiate it here, it would give you plus beta ei, and this is 0. So extremum with respect to every wi of this functional, right, gives distribution. With this would give you normalization factor, right? And the derivative with respect to beta enforces your condition. Okay? That's the meaning of, I will return to it kind of over and over, and you also learned it. And if somebody forget, maybe it's worth kind of looking into your favorite mathematical handbook. But what is now important is the following things. I now turn the table, namely, I took the Gibbs formula for entropy, and I derived Gibbs distribution as an extremum of entropy under a given fixed mean energy. Okay? And that's something which we'll be doing over and over again. At this point, physics is ended. Okay? From next week, we'll start doing information theory proper. Namely, everything else will be the same formula, but just called a very beautiful names. And we'll start doing entropy of English language, which we question.
We didn't take into account that the sum of the WI's is 1.
Good question. I just don't know. It's actually here. It's when you you can. I mean, just look in the book. I did it honestly there. Namely, that generally, of course, I do it not like this. I do it. Consider k restrictions of all possible nature. So essentially, normalization means that